Alright, my name is Muhammad Adil Iskandar bin Abdullah. My metric number is F24A1024. Today I will talk about my website is cooling rate of milk from agriculture dairy farm before packaging. Alright, in my website, like we can see, I already put some animation in it, but like we can see I can't use it in the presentation, but this is what they say, function web animation. We also in this website also I has a video and a podcast. Like we can see here, I will open it at my YouTube. This is a video.
Alright, picture this. You've just picked up a fresh bottle of milk from a local dairy farm. But before it gets to you, that milk needs to cool down fast. Otherwise, bacteria will start partying like it's spring break. So, how do we use math, specifically derivatives, to make sure our milk chills at the perfect rate? Let's dive in. Imagine the milk is at a steamy 35 degrees Celsius, and the factory wants it cooled down to 4 degrees. Here's where Newton's law of cooling comes to the rescue. The rate at which something cools is proportional to the difference between its temperature and the temperature of its surroundings. In math language, that's dt dt equal sign, kt t's, where T is the temperature of the milk, T's is the surrounding temp, and K is a constant. So let's say the surrounding temperature is 2 degrees Celsius, and our milk starts at 35. Plug those numbers in, and you get a differential equation you can actually solve. Solving it, you'll get an exponential curve that shows the milk cooling down over time. Super useful, right? This lets dairy engineers predict exactly how long the milk needs to chill before it's safe for packaging. Math is literally keeping your breakfast safe. So next time you pour milk on your cereal, remember, derivatives aren't just for tests. They're secretly working behind the scenes to keep your milk fresh. Stay curious.
Alright, that's for a video. Now we will see the podcast. It's pretty long video, like 4 minutes.
Today we're tackling a source that connects, well, a couple of things you might not expect to see together. Advanced math and milk.
That's right. Specifically, we're looking at how calculus gets used to model the way milk is made. And this is milk fresh from the dairy farm.
But I think it's maybe too long for this video. And
Wow, so let's unpack that. I mean, I definitely remember wrestling with calculus concepts back then. Differentiation.
maybe I will just stop at 1 minute.
For cooling milk, that's genuinely surprising and pretty cool, actually.
It really is. And what the source highlights so well is just how many things around us involve constant change. Temperature change is a classic example. Milk starts warm, obviously, and it needs to cool down fast for quality, for safety. But that cooling process, it doesn't happen at one steady speed.
Ah, okay, that makes sense. So the cooling rate isn't just flat, it changes. In the source, it says they use the derivative to model the rate itself, how fast the temperature is dropping at any given moment.
Exactly. The derivative is all about that instantaneous rate of change.
Yeah,
What's really key here, and the source points this out,
I hope you
is
can
that
hear
how
that.
fast it cools depends a lot on the difference in temperature. The difference between the warm milk and the cooler surroundings, or the cooling system.
Right.
As the milk gets colder, that temperature gap shrinks.
Yeah.
And so the cooling actually slows down. It's this dynamic, this changing speed that makes calculus necessary. A derivative lets you capture that speed right now, not just some average over an hour.
That's a fantastic connection.
Yeah.
So it's not just the temperature is changing, but how it's changing is complex. It needs a tool like the derivative. Okay, so the derivative gives you the speed at any instant. The source also mentions integration, right? How does that fit?
Right, yeah. Integration is kind of the flip side. If you have a function that describes that cooling rate over time, which the derivative helps you figure out, or model integration lets you add it all up, it lets you calculate the the total temperature drop over some period, or, and this is really practical for the farmer, you can use integration to figure out exactly how long how long until the milk reaches that perfect temperature, which is vital for stopping bacteria. Precisely.
So bringing this back, what does this mean?
Well, in these basic concepts, differentiation, integration, they aren't just abstract. This deep dive really shows that the rate of change modeled by the organisms how to these are the tools. They're the fundamental tools needed to understand and actually manage real physical processes like heat transfer on a dairy farm.
It really puts a practical face on those sometimes intimidating graphs and equations, doesn't it? Shows how math can describe the world, even places we wouldn't use.
Absolutely, and understanding these models, it allows for optimization too. Farmers can make sure their cooling systems are working efficiently, effectively. That directly impacts the milk quality and safety.
Right. So wrapping up this deep dive, the big takeaway from our source is that calculus gives us this precise language, a language to describe dynamic things. Milk cooling. Differentiation nails the moment-by-moment speed is constant, and integration helps figure out the total change over time to get out of it. Powerful. This is has real-world applications everywhere.
Next, the classroom straight to the farm.
So here's something to think about building on this. Thinking about this idea, rate of change. Where else might derivatives make integration to be applied to work bias, shaping the process of your everyday life?
Alright. That's all from the podcast and a video. We also has a quiz that I already made. Let's see if I can use. Oh, I can't use it here. Alright. Let's see if I can use it here. Oh, I can use it here. And let's see if I can see it. This is just a test. Yeah, you can look at this. Yeah, it will give you the answer from the what your answer. Alright. I think that's all from me. I will give to Fazrin to continue this presentation. Please, Fazrin.
There. Hello, my name is Muhammad Fazrin bin Zamri. My metric number is F24A 1137. I want to show you about my website, milk cooling rate simulation. You can see here, it is my website, so you can explore this website now. You can see here I put some animation like this. You can try. It is functionable. Secondly, you can look the video at here.
Hey, ever wondered how fast a glass of milk cools down after it's fresh from the farm? Let's talk about the math behind it, and I promise, This is way cooler than it sounds. So imagine you've just milked a cow, super fresh, and the milk is at about 37 degrees Celsius, just like the cow. But to keep it safe, that milk needs to be cooled before it's packed and shipped. Here's where Newton's law of cooling steps in. Basically, it says the rate at which the milk cools is proportional to the difference between the milk's temperature and the surrounding air. The formula? dT dt equals sign kT T underscore air. dT dt is how fast the temperature changes. T is the milk's current temperature, T underscore air is the room temp, and K is just a constant that tells us how quickly things cool off based on stuff like the container and airflow. Now, what if you could actually play with this math? Picture this: a web simulation where you drag a slider to change the room temperature, or tweak the value of K to see how insulation works. Hit start cooling and watch a graph show the milk temperature dropping over time, instantly. Maybe you even add ice in.
It's my example video. You can see here. I put the video. And lastly, I put the mathematical quiz. Cooling rate of milk using the derivative. Mathematical quiz. Cooling rate milk of using derivative. You can answer here. Put 5 question and you can sum here. I went to that's all for me. I went to pass to Zulhari.
Okay, my name is Muhammad Zulhafis bin Muhammad Zabidi. My metric number F24A 1227. Okay, I can show you my website. Use level to model cooling rate of milk from agriculture produce processing facility. Okay, we can see my video, quiz, and podcast. Okay, I can show you my video.
Agricultural processing facility, and there's a massive batch of fresh milk that's just come out, all warm and cozy from the cows. But here's the catch. Before it can be bottled and shipped, that milk needs to chill fast. Why? Because bacteria love warm milk, and nobody wants spoiled lattes. So how do the pros cool thousands of liters of milk efficiently? That's where math jumps in, and specifically, derivatives. Yup, calculus is about to make your milk safer. Let's break it down. The key idea is Newton's law of cooling. It says the rate that something cools down is proportional to the difference between its temperature and the temperature of its surroundings. In plain English, the hotter the milk compared to the chiller, the faster it cools. Mathematically, we write this as dT dt equal sign, cart T, T's. Let me decode that dT dt is the derivative. It's how fast the temperature T of the milk is changing over time TTs. That's the surrounding temp, like the chilly metal pipes or cold water it's touching. And K is just a constant that tells us how efficient the cooling setup is. Imagine your milk starts at 35 degrees Celsius and you're cooling it in a system set to 4 degrees Celsius. At first, that temperature gap is huge, so the derivative, dT dt, is a big negative number. The milk drops in temperature super fast. But as it cools closer to 4 degrees Celsius, that difference shrinks and the cooling slows down. It's like racing downhill at first, then it flattens out. Here's where it gets practical. If I want to know, how quickly is my milk cooling right now? I just plug the current temp into the formula and the derivative spits out the rate. Want the milk to hit bottling temp in under half an hour? Adjust the setup so K is bigger. Maybe colder pipes or a faster pump. Engineers use this math every day to design systems that chill milk quickly, safely, and without wasting energy. The cool part? You can predict exactly how long it'll take to reach any safe temperature just by solving the equation. So next time you pour a glass of milk, remember, behind that smooth, cold pour is a whole world of math, and a derivative making sure it's safe to drink. Stay curious and keep thinking like a scientist.
Okay, next, I can show you my quiz. Uh, Cooling rate of milk calculus application. I have five question. Okay. Next, this is my podcast. Okay. Okay, that's all for me. Thank you.
Hi, my name is Nur Munawara binti Suryanto. My matrix number is F241383. So today I want to present in my website is use derivative to model the cooling rate of milk from agricultural farm before packaging. This one is animation, food packaging optimization. This one you can adjust the volume. This you can up and down. So next is my video.
Alright, picture this. You're on a dairy farm and there's this giant tank of fresh milk, still warm from the cows. But before it gets packaged and shipped, it needs to cool down fast. Otherwise, bacteria could spoil it. So how do I model how quickly that milk chills? Let's break it down with math. There's a classic formula for this, Newton's law of cooling. It says the rate at which something cools depends on the difference between its temperature and the ambient temperature, basically how much hotter the milk is than the room. Here's what it looks like. dt equals sign kt Ta, where T is the milk's temperature. Ta is the surrounding temperature, and K is a constant that tells us how quick the cooling happens. Let's say the milk starts at 35 degrees Celsius and the room is 5 degrees Celsius. If I measure how fast the milk cools, I can use calculus to predict the exact temperature at any time. The negative sign, that just tells us the milk is losing heat. Now let's solve it. Integration time. If I separate the variables and integrate, I get TT equals sign Ta plus T rho Ta asterisk E circumflex KT TO is the starting temp. This equation lets me plug in any time T and see how cool the milk gets. But here's the wild part. Small changes in ambient temperature or that constant K can make a huge difference.
So this one is podcast video.
Okay, right. So you've given us some source material, and our mission, as always, is to really dive deep into it. This time, it's actually kind of unexpected. We're looking at modeling the cooling rate of milk, straight from the farm before it even gets packaged. And the source material specifically mentions using calculus for this. Differentiation, actually. Seems like it's aimed right at college students working through calculus. It's that connection, I think, applying this math to something so, well, agricultural. That's interesting.
Yeah, absolutely. And I think our goal here is really to pull up the main ideas, like how exactly.
And the last is quiz. Mathematics in agriculture. The answer is this one, the installation rate. Second is because 3 into gantikan kepada 5 number. This one linear function, and submit the answer. Alright, that's all. Thank you.